Hello, this is a demonstration of the program Direct Volume Rendering. David Devore and I, Rob Panloni, created it for a class project in scientific visualization. Here we have an interface for displaying volumetric data, creating a 2D image from 3D volumetric data. There's no intermediate geometric structure like marching cubes or marching tetrahedras, as were an example in assignment 3. So here we're going to read in two files. One is going to be feet, and the other is going to be a head file. It's from the National Library of Medicine, so we can go ahead and read one of the files. We'll start with the feet. It's loading. Takes a moment here. So now we have a 3D bounding box of the volumetric data. So there's points along here, evenly spaced out in 3 dimensions with float values at each point. That's the 3D volumetric data. So we can rotate with the left mouse click, and we can drag around, translate it with the right mouse click. You can zoom in and out with the mouse wheel. And then, so direct volume rendering, it uses ray tracing. So instead of looping through objects in the scene and projecting those onto the camera, we loop through the pixels. So for this, we started with projecting the 3D bounding box onto the image, and so now we have a 2D bounding box of the image plane which could contain points in the volumetric data. So we have a 2D image bounding box, and we loop through the pixels within the 2D bounding box in the image plane. So we loop through those pixels, we cast a ray out from the center of the camera eye and through the pixel and then into the 3D space. And we have a method for checking the intersect points of a ray and the 6 faces of the 3D bounding box. So we have a ray intersection with a plane, but then it's with 6 planes of the bounding, 6 planes, the 6 faces of the cube, the bounding box cube here. So we have that method. So we have the initial point where it intersects and the, say, exit point where it intersects. So say if there was like a pixel here, the enter point would be the front face, and then the exit point would be on the left face coming out there. If we shot a ray from the camera eye through the image pixel and then hit the bounding box. And then so when the ray hits the bounding box here, we composite the points along the ray. So we step through the ray as it enters the bounding box, and we use trilinear interpolation to get the float value from, say, the 8 points around it in the volumetric data. So we could be between points in the grid, and we want to look up that data. So we use trilinear interpolation for that. So we step along this ray, and we composite it. So we go from float values, and we have a transfer function to look up opacity and also the color value. So we have 2 transfer functions because we want to sum up the opacity, and when it hits 1, then we terminate. The two termination conditions are either it leaves the bounding box, or it reaches 1 for opacity, and that means light can't pass it through anymore. We've hit the end for like what light can the medium can go through. Light going through the medium. Anyway, so we also in the interface, back to the interface, we have a spline thing here. So this is the 2 transfer functions. So we can read files. We have one set up for both the feet and the head. So those are in the spline files. We're starting with the feet. So here shows the red channel, the green channel and the blue channel, and then this is the opacity channel of the opacity spline. There's 2 splines. There's a color spline, and then there's the opacity spline, and the opacity spline's for the sum up when you hit the limit of 1 to terminate. But the color spline is to just transfer it to a color. And we also sum that up as well. But anyway, so the color and shown here is actually the sum of the 3 channels, so it's the same for each point here. Yeah. Anyways, we loaded in the spline, so here's this, and then this will start the algorithm where it loops through the pixels and casts rays out, does an intersection of the bounding box, and hopefully it will transfer it to a color. Just have to sit here. So, yep, here are the feet. We have a sharpen function which kind of blends the colors a little bit better. I'm not too familiar with OpenGL, so probably we would have wanted to implement this with the ray trace thing and not have to click this a bunch. Anyways, so here is a feet from a weird angle. I'm going to rotate it to hopefully have a better angle so we can actually see the toenails, or not the toenails, but like the toes and like the intricacy of the bone structure there. So David was in charge of picking the ISO values, picking key ISO values for the transfer function, the cubic spline, to get significant data. I focused on the computer graphics side, the math for the intersection, projections, and all that. So we're doing all the projections and stuff in the CPU using a framework we developed in computer graphics class. So, oh whoops, this is not what I wanted to click. Sharpen. So here you can see the bone structure of the feet a bit better. You can see like the skin, sort of see the toenails a bit. You can see the bones, the green. You might be able to see the marrow. I'm not sure what the dark green is. But yes. So these are the feet. Let's try to read in the head. Let that sit for a second. Okay. Okay, so I think this is a different bounding box now, hopefully. We gotta also change the splines. Okay. So let's just try start off with the ray trace. I believe there's like 1 million points in the feet file and 3 million in the head, so it takes a while to run the ray trace function. So here's the front view of the skull and the head. Kind of see the bone marrow and stuff. Skull. We'll try to get a different view here. Let's rotate to the side a bit. So yeah, part of the future work for this project was to get the ray tracing done on the GPU or have it multi-threaded in the CPU. Currently it's just single-threaded, so it takes a while to run. Kind of see the ears, like the skin. Couldn't really get into the skull too much, I don't think. But yeah, you can see the teeth. So here's a side image of the skull. This is a better view, I think. Kind of see the jaw, teeth, or not the teeth, but the bone, jawbone. Here's the teeth. Kind of see some outlines of the ear. And start the spine. Let's do one more ray trace from the back. So yes, again, this is direct volume rendering done by David Devore and Rob Pantaloni for scientific visualization. You can kind of see the outline through of the eye holes on the far side from here. But yeah, the skull, the skin, ears and stuff. So yeah, this is direct volume rendering. Thank you.